We're going to illustrate the implementation of our equations associated with the least squares best fit line, the simple linear regression model, with the Ogden Valley data from our hypothesis testing days. We've reversed the x and y because it makes more sense to talk about the estimated recharge as being somehow a causal or explanatory factor in the amount of discharge that is obtained out of the aquifer. Okay. And so we have this scatter point of data, and we want to know when we push the button for our least squares line on the software tools, where is that set of numbers coming from? How does it fit that data? And what you see down here below then is one such line that has been fit through there. This is coming out of Excel, and interestingly it stops the plotting of that line at the minimum x data and stops it at the minimum or maximum x data. Right? And that's useful and important reminder to us about one of the abuses that we might have that we'll get into later on. In this case, danger of extrapolating the model beyond this range, and what are the potential implications of that. And we'll get into a little bit of that in this module, and then in the next one we'll get into it in more detail as well. Right? Note that our slope value beta 1 shows up here, and the intercept value also shows up because I chose to put an option that says display the equation on the chart. We're going to see where those two numbers exactly come from, and then although this wasn't a part, this r squared was not a part of the development of that model, we're going to talk about where that comes from too, and how that's related to some other sample statistics that we have taken a look at. Right, so in the data processing that you see here, this is the guts and glory of the calculations. And the focus here is, although the table looks like, well, how do I calculate this by hand? This is really more for illustration purposes than anything else. These are the calculations that are happening behind the scenes of the data manipulation and processing. And whether you're using Excel or whether you're using Minitab or many of the other commonly available statistical analysis packages that are out there. Right, so our focus really isn't on trying to teach you how to become really efficient calculators, because the reality is the computer will always do it faster than what you can, with the exception of just data entry of the raw data. Right? But at the end of the day, we've got to be able to interpret what comes back out. And what you're going to find in a lot of the output of these software packages, you're going to find some of these summary numbers, and interpreting those, understanding those, what they're telling you is going to be crucial too. So having a good idea about how to do this by hand in some sort of concept, and then is going to aid towards the interpretation later on and help to understand in this blizzard of alphabet soup that we're going to have what all that means, and piecing it apart in some sort of meaningful way comes back to sort of, in a sense, physically understanding how to construct the data and what we're doing there. Okay, so this first real column here outside of our joint pair, this is just the year the data was collected, is just a simple product of x times y, and then squaring the x value, squaring the y value, and the residuals will come back later. Here's just the residual, here's the square the residual. So these last two columns, let's not focus on just yet. I wrote down here at the bottom just a reminder about what this row does, which is the sum of whatever's in that column. Right? So we have 17 data points. Of course, this number will be the same because they're paired data. And there's our sum of the x's, there's our sum of the y's, there's the sum of the xy's, and etc. on down. Now notice that the sum of the residuals, by the way, is essentially 0, which is about what they should be, right? Because we're trying to minimize that error. What we're really doing is trying to minimize the squared error, with the result that we have an aggregate error of 0. It tells you again that averages don't tell you a whole lot, because that's essentially the average error that we have here. Well, average error is 0, but look, it's not a perfect fit. We still have some leftover unexplained variability sitting out here. Okay. And as we move on down in this particular table, then we've got then a sample average 13.31, a sample average of 13.35 for the x and the y, and the standard deviation that you see here in this case is coming straight out of Excel, and that is the n-1 version. That's just a useful thing to keep in mind. That's lowercase s sub x and lowercase s sub y. And you do have to keep very careful track of the various uppercases, lowercases, and how many subscripts you have. It's sort of a crummy deal, but it is reality that you have to do that. Now the other thing that you see here is the number of digits and decimal places that are retained doesn't appear to be all that many. Of course, the software is including a lot more than that, and this is one of those situations where if you process data by hand, you do want to keep an inordinately large number of decimal places. You sort of disobey all of the practical engineering rules that we have about significant digits when you're processing this particular data, and it does tend to be important to retain as much as you can. I've not here in terms of the printout, but only because it makes it much more difficult to talk about these numbers to you if I include too much. Okay, so what we have then down below, and remember our goal is finding the slope beta 1, finding the slope beta naught, or the intercept beta naught, is we're working with some of these sum of squares kinds of numbers, these things up in here, right? And so I've labeled them capital S sub XX, capital S sub YY for a very specific reason, and maybe that's to confuse you, because that's sometimes what it seems like we end up doing all the time, right?